we can start the session. We will start from the student on the left. We have the common source amplifier given in this question, and the values of device parameters for PMOS are given as. Channel wave modulation comprise 0 volts and VDT standard. Okay. And the rest of the components are R1 is equal to 20 kilo ohm, R2 is 20, RD is 4 kilo ohm, RS is 500, C1, C2 are 10 micro ohm, 100 picofarad respectively. These are the values. Now, what we need to do is, by calculating the output resistance of the circuit, we need to find the output resistance first, find the upper cutoff frequency of the amplifier. Okay. Assume the parasitic capacitances are negligible and CGS, that is CGS and CGD values are negligible. Select the closest option from the following. So, what we'll do is simply so this is what we will do. First, we will draw the equivalent circuit of the circuit shown in figure 5.2, and then we will attach a test source as the output and find the R out. So this is the first question, and we will ignore the CGS and CGD values. Fine. Let me just first draw the equivalent circuit. So I have, let me just first draw first all the components including the capacitance. I have V source, I have RS, then I have a capacitance of C1, then we will have R1 parallel R2. Alright, then sorry, source grounded. So this is my, so I can write current in this direction and I should write GMVGS. Otherwise, it is from source to drain in the PMOS. Then it should be GMVHG. Just be careful with the sign. We have drawn the equivalent circuit. Now we need to find the output resistance corresponding to the capacitance, output capacitance. So we will have this resistance. And when we find this, we will attach a test source of Vx and Ix. And you know, you know, so we need to short them. So my equivalent circuit becomes, and also shorting. Let's- So if this is zero, which will be zero, this is grounded. This is also grounded, so there will be only current here. So what I'm left with is RD. And my R out, that is Vx by Ix, will be RD. So this is my output resistance. Now I have found the output resistance. What is the next step? Upper cutoff frequency. Therefore, will be given by 1 by 2 pi C out times R out, right? Here R out is RD, and C out is a combination of this capacitance, right? This is a total output capacitance. CL is 100 pico, correct? So I can say that, and C1 is 10 microfarad. So the output frequency will be dominated by this frequency, this capacitance, alright? So this will be 2 pi 100 pico multiplied by R out, that is RD, which is 4 kilo. Calculate it, and you will get an answer of 0.1. Alright, this is how we do it as simple algebra. Okay, next is find the gain from gate to drain and omega is 100 kiloradian per second for the circuit shown figure. Again, we have to treat them as negligible, the parasitic relations. Select the closest option. We know this will be my gain, and now I need to find Gm, which I will write directly as determined by VGS minus VTH. Okay, let's see what is the value of G. This is R2 by R1 and R2 divided by R1 plus R2 multiplied by VDD. R2 is 80 kilo, R1 is 20, and VDD is 10. So Vg is 80 by 8 volt. Vg is 8 volt. Now I need to calculate Gs. That is Vk minus Vs. You know that this is PMOS and your VDD is your Vx, which is 10 volt. So it will be 8 minus 10. This is minus 2 volt. Okay. So my Gm Kw/L is 2 milli. And VGS we need to write VSG or PMOS will be 2 minus VTH2, that is minus 1, which write the magnitude of it is 1. So Gm is 2 millisiemens. Now G is equivalent to then 2 millisiemens multiplied by RD, which is 9.4 kilo. That is 8, which has a sign of negative. So it is minus 8. Option C. So moving to the next part. Let me first check the So this is it. Now again we need to find Yes. So we need to calculate effective input capacitance. That means we need to consider the parasitic capacitance. By using the Miller theorem. Now, let me just quickly draw the equivalent circuit. Okay, so this is how your parasitic capacitances are present in your equivalent circuit. So what we need to do is we need to calculate the effective input capacitance. In the last session, we calculated it from the Miller's theorem. Effective input capacitance will be CGS plus CGD 1 minus A, where A is the gain of the transistor, which we calculated as minus 8, right? From previous question. Okay, now the values of CGS and CGD are given. We can calculate this C input. So just remember that if I convert this into the effective capacitance, it will be like this. CGS in parallel CGD multiplied by 1 minus A. So you decouple the CGD capacitance and one of the components will be at the output part. So one will go here and one will be at the output, which we need to calculate. Sorry, we need to just calculate the input inductance pressure. So my C input, which is effective, will be picofarad for CGD, that is 6 picofarad, 1 minus 8, that is plus 8, 9. So calculate it, it comes out to be 66 picofarad. So this is your answer. Right? Yes. We'll take a 2 3 minutes break and we'll just we can skip to the Okay, so we have calculated the effective input capacities. Then we can calculate C N effector is 66 picofarad. Now we can calculate the lower cutoff frequency, which will be given by R input C input. And if I look at this, if I look at this equivalent circuit, my R input is R1 parallel R2 plus this resistor, which is series resistance. Current parallel RT is 80 kilo ohm, 20 kilo ohm, the 80 plus 20 is 100 kilo ohm. It's RF. This is 500 ohm. That is 5K. Comes out to be 1600 by 100K. So it will be 16K plus 0.5K, which is 16.5K. So this is the total input resistance. Now we substitute it here with C and S 66K. You can find the lower cut of it. It's calculated and match with the values which are sent. Okay, so now this is done. Now we have another thing. We need to calculate the upper cut off. Here another thing we need to be careful about this. Here we calculated it with respect to. I did wrong here. So this is with respect to C1. So this input resistance, this is for C1. Now, if we want to calculate it for C input, that is this resistance, which is CGS parallel CGD divided by 1 minus A. Just look here, for C input, we have RS like this. This is R1 parallel R2, and I have a capacity C input. So it is actually R1 parallel R2, that is 16K. So R effective, let me call it as resistance of R effective. It will be 16K, which is R1 parallel R2 parallel RS, that is 0.5 kilo ohm. So use this resistance R effective to calculate another pole. Okay, this frequency is actually a pole. Let me call it P1, and another P2 will be 1 by 2 pi R effective C in. See which of the value is lesser is your lower cutoff frequency. Okay, so where you will observe this behavior, let's say I plot a gain, and when it strikes a lower cutoff frequency, let me call it P1, the gain starts reducing by 20 dB, 20K. Let me just make this on the board plot. Let's say there is only a single pole. If there are multiple poles, it will again drop. Let's say there is a pole here with 40 dB per decay. Now, if it is a zero, then the slope will again increase. Okay. So maybe you may have studied in control systems. So, so calculate these two poles, P1 and P2, and find out which one is lesser, and that will be your cutoff frequency. Now, on to the 10th question. That is the last part of. Okay, last part of this circuit. That's upper cutoff frequency. And for that, we will calculate output effective capacitance first. As told, if I have Z here and the amplifier of gain A, so this can be translated into amplifier of gain A, Z1 and Z2. Okay. Now, if it was capacitance, so my Z1 that is for the capacitance C1 here. Let me call this it as a C1, which will be let me call it CZ1. CZ1 is equal to CZ1 minus A, and CZ2, which is at the output, will be CZ1 minus 1 by A. So here output capacitance will be then, therefore C out effective will be existing capacitance. Sorry, there is no existing capacitance. Let's say there is no existing capacitance for now. Or there is. Yes, there is, right? There is a capacitance of CL, this CL, which will be in parallel of the capacitance we will calculate that. It will be CL plus CGD times 1 minus 1 by A, right? So my total output effective capacitance will be CL, that is 100 picofarad plus CGD is 6 picofarad, 1 minus 1 by 8 minus 8, so it will be 1 plus 1 by 8. So it comes out to be 100 picofarad plus 6.75 picofarad. That is 1 over 6.75 picofarad. Therefore, upper cutoff frequency will be 2 pi times R out, which we calculated in the first step, multiply by CR. That is 2 pi R out, which is directly RD, that is 4 kilo ohm, multiply CR, which is 1 over 6.75. So this will give you upper cutoff frequency. Alright, I hope it is clear. Now, slightly different questions. What we studied till now is how to calculate the cutoff frequencies. Now, the rest of the questions, let's see what we will learn. Again, as usual, we will start from the BJT and then we will do some questions on MOSFET. Okay. So first, this is a PNP. The values of the device parameter for PNP transistor are given VB and VEC SAT is 0.3. Beta is 100. Early voltage is 60. C pi, these are the parasitic capacitances are 10 pico and 5 pico. CL, long capacitance as earlier in the earlier question, it was also CL 100 picofarad in this as well. Supply voltage is 10 volt, RS is 100 kilo ohm, RE these are 10 and 2 kilo ohm respectively. So by considering the DC current analysis, find the maximum output signal swing without significant distortion for input sinusoidal signal amplifier circuit shown in figure 6.1. So we need to find signal swing peak to peak voltage such that the signal is not distorted. Alright. First, we will calculate 2 points. That is Houston points, which is VC, VE, IDSC. Okay, so this will follow a KVL. So we start for VCC minus current flowing for RE will give a potential drop of IER minus VBE, VEB, okay, and we will have base current of IB such that the potential drop will be IBRS and it will be equivalent to VBB. Okay, VCC is 10 volt and VBB is 4 volts, so it will be 6 equivalent to I is IC plus IB times RE plus right, 6 minus VEB, VEB is 0.6, so it will be 5.4 is equivalent to IC is beta plus 1, sorry, IC is beta times ID, so it will be beta plus 1 RE plus RS whole multiplied by IB. So I can write IB as 5.4 divided by beta plus 1 RE plus RS, that is beta is 20, so it will be 101 multiplied by RE. RE is 10 kilo ohm plus RS is 100 kilo ohm. If you calculate it, IB comes out to be approximately 5.0. So now I have IB of 5 microampere. Now electric current IC will be beta times IB, that is 100 multiplied by 5 microampere will be 0.5 milliampere, right? So it will be used to calculate collective potential. RC kilo ohm. That is 1 volt. And similarly, we need to calculate the emitter potential, which can be given from the Ohm's law as VCC minus IERE is equal to VE, which is VCC minus IERE is equal to VE. So VE is equivalent to 10 minus, let's assume IA is equivalent to IC, so it will be zero point 0.5 milli multiplied by RE. RE is 10 kilo ohm. So what do we have? VC is equal to 1 volt and VE is equal to 5 volt. Now we need to check the signal sweep. For that, we have two conditions. One, VCC is 10 volt and VE sat, VEC sat is 0.3 volt. So your potentials at VE minus VC should be within this range. First, let me draw a reference of 10 volt, which is the maximum VE can go without going into the cutoff region. Because if VE is equivalent to 10 volt, current will drop to 0. And I have this is ground, this is 0, and on top of it, we have a VC potential of 1 volt. Now, VE can change with the input voltage, input sinusoidal signal. So, to keep the device in saturation, VEC should always be greater than 0.3. That is VE sat. So, I will draw a line here. I will draw a line here, which is which has a total value of 3 volt between this line and the VC. So the maximum swing on the lower side can go to 5 volt minus 1 minus 0.3. How much is it? 3.7, right? So a signal, and what is the maximum in the above? That is 5. So always remember that when you check the signal peak to peak voltage without distortion, choose the minimum one. So a signal without distortion, it will have a peak to peak voltage of 2 times 8.7 volts. That is 6.4, 7.4, sorry. So the signal will be let's say like this. Okay, so this was about this. And then we have in this question is now in this part, voltage change at node B and C will also be considered. So for this case, we have VEC of zero point 0.3 for saturation. This is given. That means VE minus VC is 0.3 with VE will be given by 10 minus IE RE minus VC will be given by IC RC is equivalent to 0.3 volt, which again if we assume IC is equal to RC, IC is equal to IE, we can calculate 10 is equivalent to 10 minus 12. 12 comes to RE plus RC is equivalent to, okay, RE is 10 ohm, RC is 12, so it will be 12 kilo ohm total. So this is 12 IC, 12K IC. So IC is 10 minus 0.3 divided by 12K, 9.7 milli by 12. That comes out to be 0.808 milliampere. So now for this case, for the device to be in saturation, this is the minimum value, minimum condition. For this minimum, I current flowing should be 0.808 milliampere, and corresponding to which potentials are VE is equivalent to VCC minus IERE is equivalent to 10 minus 0.808 milli multiplied by 10 kilo ohm, that is RE resistance. It okay, comes out to be 1.92 volt. Similarly, as given VEC is equal to zero point 0.3, we have 1.92 minus VC is equivalent to 0.3. Therefore, VC is equivalent to 1.92 minus zero point 0.3, which will be equivalent to 1.62. So these values are the peak voltages, instantaneous voltages for VE and PC. Now, if I draw again the references where this is my VCC of 10 volt and this is my ground plane of 0 volt. This is DC equivalent voltage of 5 volt. Alright. In the previous part, we didn't consider the AC instantaneous voltage swing in the at these nodes. But in this question, we need to answer that. And then we have VC of 1 volt, and on top of it, we will have a swing with a maximum value of, this is 1 volt. In total, it will be 1.992. Sorry, 1.62. Now, if this is 1.62, I need a cushion of zero point 0.3 volt, right? 0.3 volt here, and thus also with this it will have swing like this, right? So how much is this? Sorry, this is like this, right? And this is at this peak. So this is how your waveform will look like. What will be the value for this? This is 5 minus 0.3 minus 1.62. That is equivalent to 5 minus 0.3 minus 1.62, 3.08. No. And if I multiply it with the 2, so this, we peak to peak voltage of 6.161. So this is when we take the fluctuation of the node into consideration as well. Okay, now this is a good question because it will be a good practice. Find the input voltages. We have done a lot of questions of this type. It says that without considering RS. So you know the circuit? Circuit is, this is the circuit. We need to draw the equivalent circuit for it. Alright, let me draw. Ignoring the RS, I have, let me just first draw the equivalent circuit, then we will look. Now, if I need to calculate the input resistance, let me call it Rin. I will attach a source of VXIX here, or directly IB. Let me just call for now it as VXIX. So we'll have our input as Vx by Ix, right? Where Ix will be, this is VB, this is E, which is equivalent to V out. So I can write VB minus V out by R pi. And we know R pi is beta by Gm, and Gm is I2 by Vt. Just remember these formulas. Okay, so my R input would be VB. Let me just call these notations as VBIB so it will not confuse us. Okay, VB by IB. That means it will be R pi by VB minus V out, which is equivalent to R pi divided by 1 minus V output by VB. Now what we need to calculate is we need to calculate V output by VB. Okay, now nodal analysis. Output node. Okay, we need to do the nodal analysis here. So what we will have, V output by RE is one component. Current IB incoming is one. We will have a component here. Let me see. This is like this, and this will be GMVPE. Okay. These are the components. So I will write here V output. What I have done here is R pi is equivalent to beta by GM, or I can directly write R pi is equivalent to PV by IB. Okay. This is because potential across this is VBE, current flowing is IB, so I can write VBE is equal to IB R pi. So this is what I have written here. So VBE is equivalent to VB minus VR. So simplifying it, I will get plus taking V out common here, here and here. So I can calculate V output by VB, which will be by R count plus G divided by 1 by R plus 1 by R naught plus 1 by R count plus G, right? These values are very large, so I can assume the output by VB is nearly equivalent to Gm divided by 1 by RE plus Gm. Gm is the calculated Gm, right? Now, Gm is IC by VT, and we know IC is 0.808 milliampere by 26 millivolt. Milli and milli will cancel. Gm is 0.808 divided by 26. Multiply by 1 by RE. RE is given, that is 1 by 10K, plus Gm, that is 0.808. So this value comes out to be 0.995. Now, if I know this value now, I can substitute it here and calculate my R input. V out by VB is 0.995 and R pi is beta by GM. Now you know GM, R pi will be beta by GM, and you can calculate this value. Okay, so we'll just write the answer. It comes around 1 mega ohm. Okay, gain. Here we need to calculate the output by V input. So what we will do is we know this value, V output by VB, calculated, right? 0.995. And what about this is known, this is 0.995. And what about this? VB by V input. Let's go back to the circuit. This is V input. We need to compute VB. So it will be from this. So we have, so therefore VB will be equivalent to R input divided by R input plus RS times V. So VB by V input will be, so this will be equivalent to 215 multiplied by R input plus RS. Right? Construe the values. We calculated R input. R input we will calculate from this here, that is around 1 mega. And then you know the other value as well. That is RS, substituted and calculated again. Here it's given that we need to consider the effect of RS. Moving on, we have a question on MOSFET. The circuit shown in figure 6.2 is a common drain amplifier. Okay. The values of the device parameters are given. Initial voltage is 1, kW is 2, some wave modulation, and these parasitic capacitances are given. Find the transconductance. First, IDS, right? So this will be kWL, that is 2 milli. VGS. Now VGS is not directly possible, so you need to write VG minus VS. That is your V out here, because this is the source, minus V2, that is 1. And what is VG? R2 divided by R1 plus R2 multiplied by VDD. So VGG R2 is 5 kilo divided by 5 kilo plus 5 kilo multiplied by 10. So VG is 5 volts. So my GM is 2 milli. 5 minus 1 is 4. 4 minus V0. So this is my GM. But for this to be calculated, we need V0. So that will be calculated from IDS. So my IDS is kWL. And how can I write IDS as here? For load resistance RL, current of IDS is flowing, so V0 is IDS RL as well. So on the left hand side, I can write it as V0 by RL is equivalent to 1 milli 16.9 plus V0 square minus 8 times V0. This is a quadratic equation. So this is V0. RL is 2 kilo. So this is 2 basically. 2 into 16. Okay, let me just see one more step. So this is actually 2 V0 square minus 8 V0 minus this is 9 V0 9 plus 32 equivalent to 0. Yes, 262. It will be total of 70. So this is the quadratic equation. To solve this, you will get two answers: 5.7 volt and 2.81 volt. This is a quadratic equation. Now, which one to choose? Now, if I choose V naught is equivalent to 5.7 volt, your VG is 5 volt. This implies VGS will be 5 minus 5.7, that is minus 7.7. This is off. So this is not possible. So therefore, V naught is equivalent to 2.81 volt. So when V naught is 2.81 volt, therefore GM will be 2 milli 4 minus 2.81, which comes out to be 2.38 millisieverts. So now you have calculated the GM which was required in this machine. And now the last part is voltage gain, which will be simple. I need to draw balance circuit. This is slightly different than what we calculate, that is MRD. Slight bit of calculations. Do the nodal analysis at node A. We get V naught by RL plus V naught by R naught. I'm supposing the current is flowing in this direction, and the total incoming current will be GMVGS, right? So taking common, V naught by RL plus R naught. What is GMVGS? This is the input minus V output. So V output is basically this is your final answer. Calculate the values and find the gain. So I guess that's it for this week. We will meet again on the Saturday.